Hi, my name's Grace Sod, and this is my Physics 2211 Lab 1 report, and in this lab we're going to look at constant velocity. So, an overview of the lab, the topics we covered are Newton's first law, which is an object at rest or in motion will remain in rest or in motion until acted upon by a force. And this basically describes the constant velocity that we're going to see from our moving object. We also are going to have a constant and zero net force. However, in the experiment, we're going to see that that's not actually the case, and we will experience a friction force. Equations we use here, just change in position over change in time to find the initial velocity, and then position update formula and velocity update formula. We use both of those in our iterations in the code. So this is the raw video that we filmed for the experiment. I just rolled the water bottle across some concrete stairs. You can see moves in a relatively straight line, and it appears to be relative constant velocity. In the next slide, this is our tracker video. You can see that the video is a lot shorter. That's because I had to cut out the beginning and the end, because in the beginning, the water bottle was still accelerating, and in the end, the water bottle was really starting to decelerate. So I cut those points out so I could just get to the constant velocity part. And I only used frames 79 through 110, and delta t between each frame was 0.0 through 3 seconds. The calibration, we used the diameter of the water bottle, which was 0.03 meters. And then the axis, we just had the water bottle start at the origin and then move in the positive x direction. So changes we made to the starter code, with the initial conditions, we changed the mass to 0.54 kilograms. This was the estimated mass of my water bottle. And then we had the initial velocity vector as 0.7300. The y and z components remain 0 because the bottle was only moving along the x-axis. And I used the first and second time step of the tracker video to calculate the initial velocity. And for this one, we got 0.73 meters per second. And then the ball.POS, which is the position, we kept that as 000 because it started from the origin. And I kept delta t as 0.01 as well. And then changes we made to the while loop iterations, we changed the condition to t less than 1.035. This is because 1.035 seconds was the stopping time of the tracker video. So that's how long the tracker video, that was the duration of the tracker video. And then the ball.vel, we used the velocity update formula. However, fnet in this case was always going to remain as 0. So the velocity never actually changed with each iteration, but the position did change with each iteration, and we used the position update formula to calculate this each time. And I'm going to show you the model, how it runs. As you can see, the ball moves to the right, and we have our position versus time graph showing our constant velocity. So this is the comparative graph. The blue being the model and the purple being the experiment. As you can see, they're not the same. This is to be expected because the computer accurately depicts constant velocity, while the experiment, there are some other factors that cause the water bottle to not have an exactly constant velocity. And we can tell that it has a constant velocity by the fact that the slope of the model line is the same, while you can see the slope of the experimental line kind of dwindles off and it decreases. So why does this happen? This is because the water bottle does slow down, and this is caused by the friction force. So as you can see in the top right corner, we have the velocity vector, and then the friction force vector always moves in the opposite direction of motion. So this force acting upon the water bottle is going to cause the velocity vector to become smaller and slow down. Another thing to consider is the mass of the water bottle is inconsistent. So although we marked the center of mass of the water bottle being the center of the edge, that's actually not the case because the cap weighs less than the body. This will cause a change in the z coordinate. You may have been able to see in the video, the water bottle did move a little bit closer towards the camera as time went on. So that's because the center of mass is not exactly in the center. And that is all I have for this lab. Thank you for listening.